Welcome back to the deep dive. Today we're doing the ultimate self-inventory. And no, not your finances or life goals. We are diving deep into, well, the most complex machine in the known universe.
The one you're sitting in right now.
Exactly, the human body.
And we're really going to treat it as a masterpiece of biological engineering. We've been looking at sources that reveal this astonishing hidden infrastructure, the massive scales, the raw efficiency that keeps you alive.
And that's really the main for this deep dive. We want to take those facts you might sort of remember from biology class and turn them into real aha moments.
We're going under the skin to find the engineering secrets, the shocking stats that show the sheer logistics of just existing.
It's a huge topic.
It is, and it's vital to frame this right. You are not some fixed, solid mass. You're a dynamic, liquid-cooled, electrically governed system. And the scale, I mean, we have to use astronomical comparisons just to get our heads around it.
Okay, so let's unpack that. And I think the best place to start is the ultimate logistics challenge, the circulatory system.
The superhighway of the body.
Totally. And the engine, your heart, it's just relentless. It beats over 100,000 times every single day.
That work rate it's all about high volume. Think about the fluid movement. In 24 hours, the heart pumps more than 2,000 gallons of blood.
2,000 gallons.
And it's running two operations at once. You have the right side sending blood to the lungs for a refill on oxygen, and then the much more muscular left side is pushing that fresh supply back out to the body.
And where that blood has to go is, well, it's unbelievable. I think this fact really deserves a pause. The total length of all your blood vessels.
Arteries, veins, all of it.
And the tiny capillaries, it all comes out to about 60,000 miles.
60,000
Yeah.
miles. To put that in context for you, the circumference of the Earth at the equator is just under 25,000 miles.
So you could circle the planet.
You could circle the entire planet, yeah, roughly 2.5 times if you stretch them all out.
That is just mind-bending packaging efficiency. But, okay, that huge network needs a constant oxygen refill, which brings us to the lungs.
Right, the ultimate achievement in biological surface area.
So how much air are we talking about?
An average adult breathes in about 11,000 liters of air a day. That's around 22,000 breaths. And they're so specialized for holding air that they're actually the only organ that can float on water.
Because of all the air trapped inside.
Exactly, inside millions of tiny air sacs called the alveoli.
And the number is staggering, right? Something like 300 to 500 million of them in each lung.
And here's that second shocking surface area number. If you could take all those microscopic alveoli and stretch them out flat, you'd cover an area about the size of one complete side of a tennis court, 70 to 80 square meters.
Wow.
And that scale isn't random. It is absolutely necessary for the rapid gas exchange you need to fuel that 60,000-mile superhighway.
It makes sense. High mileage requires high fuel throughput. Okay, let's go back to the engine itself, the heart. It's circulating about 5 liters of blood a minute, beating, what, 75 times a minute?
Roughly, yes. And we think of it as this incredibly powerful, tireless machine.
But it's not powerful in the way we think, is it?
No, and this is what's so fascinating. The sources estimate the average mechanical power output of an adult heart is surprisingly low. About 1 watt.
1 watt? Seriously? That's not even enough to run my phone charger. How is that possible for an entire body?
It's the definition of efficiency. It's optimized for duration, not for, explosive force. It's all about consistent work.
So it adds up over time.
A lot. That 1 watt running continuously over a 70-year lifespan adds up to somewhere between 2 and 3 billion joules of work. The marvel isn't its raw power, it's the unmatched consistency.
Okay, so the heart handles the pumping, but that all needs a solid framework. Let's shift from liquid logistics to our bones, specifically the femur.
The thigh bone, yeah. Longest and largest in the body.
It has to be incredibly strong.
Oh, immensely. An adult male femur can support up to 30 times the weight of an adult. We're talking about 6,000 pounds of compressive force.
But its real secret is that its strength isn't the same in every direction.
Exactly. That seems like a design flaw, but it's actually a feature. It's optimized. The material is what we call anisotropic. Meaning its strength depends on the direction of the force. Its compressive strength resisting being crushed along its length is incredibly high, 205 megapascals.
But what about pulling or bending?
That's where it's weaker. Its tensile strength, resisting being stretched or torn, is way lower. Only 135 megapascals.
So it's built like an architectural column. It's great at handling weight pushing down, but
Yeah.
not so great at being pulled or twisted.
Precisely. which explains why the #1 cause of femur fractures is a motor vehicle collision. The failure isn't the bone getting crushed, it's the bending or twisting force that starts to crack on the tension side, where it's weakest.
That's a powerful lesson in material science right there. Now, what about the control system for all of this? How fast do the instructions travel?
Incredibly fast. The main nerve signals, the myelinated ones, can travel up to 300 miles per hour, faster than many race cars.
And yet, with all that speed, we are only consciously aware of a tiny fraction of what's going on.
That's the core of biological efficiency. Studies suggest something like 95% of our daily biological governance, heart rhythm, breathing, blood pressure, is handled unconsciously.
By the autonomic nervous system?
The ANS, yes. It has to be this way, really. It comes down to energy. Your brain is only about 2% of your body mass, but it is an absolute power hog.
It uses 20% of the body's total energy.
Right. So you have to delegate all that routine maintenance to the ANS to free up the brain for, high-level thinking and decision-making.
And some systems even have their own local government, so to speak, like the enteric nervous system.
The second brain.
Yeah.
The digestive system is just so complex it needs its own dedicated control system. The ENS handles things like muscle contractions to move food, hormone production, and it does it almost completely on its own, independent of the central nervous system.
Which really explains that gut feeling people talk about.
Absolutely. The gut-brain axis is a two-way street. Irritation in your gut sends powerful signals to your brain that can trigger real mood changes. Nervousness, sadness, fear. When you feel anxiety in the pit of your stomach, that's literally your second brain talking to your first.
And that second brain has to manage one of the most hostile chemical environments in the body. The stomach is basically a war zone.
It really is. The gastric acid in there, which is mostly hydrochloric acid, has a pH between 1 and 3.
So extremely acidic.
Extremely. It has to be. To break down food and, maybe more importantly, to kill off any nasty bacteria you might ingest. A pH below 3 will kill most bacteria in under 15 minutes.
So how does the stomach not just digest itself?
It's got a brilliant two-part defense system. First, a really thick layer of protective mucus, and second, it secretes an alkaline bicarbonate right at the stomach wall. It's a buffer that neutralizes the acid right where it touches the tissue.
That sounds like a lot of work, metabolically speaking. Does it affect the rest of the body?
It does. This is where it gets really cool. The sheer metabolic cost of making all that acid causes a systemic effect. As the stomach cells pump acid in, they have to dump alkaline bicarbonate out into the bloodstream. This causes a temporary, measurable rise in your overall blood pH.
And that's what scientists call the alkaline tide.
That's it. It's part of why you might feel a bit sluggish after a big meal. The chemical battle in your stomach is literally changing the chemistry of your entire blood supply for a short time.
Okay, let's shift scale again down to the cellular level and bust a big myth. For years, we heard that microbial cells in our body outnumber human cells 10 to 1.
Yeah, that old ratio was based on some pretty flawed early calculations. The current, more accurate estimate is much closer to 1 to 1.
It's about 1.3 microbial cells for every human cell.
Right. About 38 trillion bacteria to 30 trillion human cells.
And why did our cell count jump up so much in that revision?
It's mostly down to blood cells. The vast majority of our cells, something like 90%, are short-lived blood cells. A red blood cell, for instance, only lasts about 4 months before it gets replaced.
Okay, so now let's talk about the blueprint inside those cells. We know the DNA in a single human cell is about 2 meters long. What happens when you multiply that across 30 trillion cells?
You get a number that is just almost incomprehensible. The collective length of all the nuclear DNA in one human body is calculated to be about 6.2 billion kilometers.
6 billion kilometers! I can't even...
This is where we need those astronomical comparisons again. That length of genetic code is enough to stretch from the Earth to the Sun.
Okay.
More than 41 times.
41 round trips to the sun, basically, all packed inside you. That is peak biological packaging.
It really is.
But let's talk about a downside to genetics, a really unsettling new finding about aging. It involves mitochondria.
The powerhouses of the cell. Right.
Yeah.
So mitochondria are descendants of ancient bacteria, and they still have their own small circular DNA.
And the phenomenon is called NUMtogenesis.
NUMtogenesis, yes. It's where bits of that mitochondrial DNA, these NUMTs, actually get inserted into our main nuclear chromosomes. We used to think this was just an ancient evolutionary thing.
But the sources we looked at say it's still happening. Right now. In us.
It is. Researchers found this insertion process is happening frequently in our neurons. especially in non-dividing cells like those in the brain's prefrontal cortex. It happens several times during a person's lifespan.
We're still accumulating junk DNA from our ancient bacterial ancestors.
Pretty much. And here's the link to aging. A higher accumulation of these NUMTs in the prefrontal cortex was directly correlated with people who died earlier.
And there's a trigger for it.
Stress. High physiological stress makes mitochondria dysfunctional, and in stressed cells, this NUMT accumulation happens 4 to 5 times faster. So you can add genome instability to the long list of reasons why chronic stress is bad for you.
That puts a whole new light on managing stress, knowing it's accelerating the buildup of genetic junk in your brain.
Exactly. It connects everything we've talked about, the emotional and the chemical, directly to our physical durability over time.
Okay, before we wrap up, let's quickly hit a few classic anatomy myths that distract from these incredible true facts. We already debunked the 10% brain myth.
Right. Your brain is a power-hungry organ using 20% of your energy. And any damage, even to a tiny part, has severe consequences. It's a fully utilized system.
What about cracking your knuckles causing arthritis?
Totally refuted. That pop you hear is harmless. It's just gas bubbles bursting in the fluid in your joints. Study after study has shown zero link to arthritis.
And the last one, the idea that muscle turns into fat if you stop working out.
Another persistent one. But muscle cells and fat cells are completely different tissues. They can't convert into one another. What really happens is you get two things at once. Muscle loss from inactivity, that's atrophy, and you might gain fat if your diet doesn't change.
But one doesn't become the other?
No, there's separate transactions. There's no transmutation.
So after this whole deep dive, what's the big takeaway? For me, it's that your body is the system of extraordinary silent efficiency. It's all happening beyond our conscious awareness.
From the 1-watt heart driving a network that could circle the
To
Earth.
nerve signals faster than a race car, it's all just running in the background.
And what's really come to light is this fundamental biological trade-off. The body is constantly balancing the need for renewal, like your skin cells being replaced every few weeks, against the need for structural integrity.
In the more critical systems.
Exactly. Cells in your central nervous system or your heart muscle, they replace themselves very, very slowly. They have to maintain their complex, organized structure and function.
Which brings up a really fascinating, almost existential final thought.
Well, if those cells we rely on most, the heart muscle, the critical brain neurons, if they replace themselves so slowly to maintain that integrity, what does it truly mean for our long-term health that those practically irreplaceable cells are constantly accumulating this vestigial genetic junk from our ancient bacterial past?
Are we basically hardwired to carry the history of life as a kind of ticking clock inside us?
It's definitely something for you to ponder as you go about your day, powered by that astonishing 1-watt engine.